Hello and welcome to episode 3 of Mr. M's Math Games and Math Breakthroughs. Today we're going to learn a game called Roll and Subtract 1000, and we're going to learn about one of the oldest theorems about right triangles. This is a theorem that is true about any right triangle ever, and it is very famous. I'm sure you've heard of a squared plus b squared equals c squared. If you haven't, we're going to learn about today, and it is the Pythagoras Theorem. But first, I'm going to change the direction of the camera so that you can see my computer, and we're going to learn how to play roll and subtract 1000. Let's get started. All right, so here we are on our Schoology page, and I'm in this week's folder, September 28th. I will click on today's date, which is Wednesday, September 30th. And you're going to see a folder called Roll and Subtract 1000 Game Materials, which is the game we are learning today. And I'm going to click on this PowerPoint. And when I filmed this, it didn't finish loading. So you're going to see something different. It's going to try to load the PowerPoint, and make sure to click the download button. It's the arrow that we pressed last time, but I'm going to download the file this way. So you're going to see something different. So I'm going to press OK. This is going to open up the PowerPoint, and we're going to do something very similar to we did last time, which was clicking the enable editing so that we can actually play the game. So we're going to wait for that to open up. Here we go. You might have noticed that I changed my shirt. I filmed this on Sunday, so I was wearing my Seahawks stuff, and now I'm wearing my Sounders stuff because they're playing soon. All right, so we're going to click Enable Editing. You can see that here. And so what I did here was I actually added some dice here, and it's in the PowerPoint, so you don't have to go anywhere else to roll these dice. So you might be thinking about this game. It's called Roll and Subtract 1000. So what do you think the point of this game might be? So go ahead and think about that for a second. Noticing what you have on the screen, right? So you can play this game with either one person or two people. Either way is fine. I'm going to show you how to play with one person. I'll talk a little bit about how it might look like with two. So I'm going to write here my name, I'm just going to put Mr. Maldonado. And so here you start off with 1000, and you're trying to get as close to 0 as possible. So whoever's closest to 0, if you're playing with somebody else, is the winner. If you want to just challenge yourself, you want to get to exactly 0. So what's going to happen is that I'm going to roll these 3 dice. Now how you roll these dice is you go over them, and you're going to press this play button. And press play. And now I'm going to stop it. Actually, you know what? I'm going to make this a whole big here. Let's make it big. So I'm going to go here, press play, and press play. So now these are all, right, they're rolling. So I'm going to press pause here, pause. All right, so I got a 1, a 6, and a 1. All right, so I'm going to go here. So I have a 1, a 6, and a 1. So what's going to happen now? A 1, a 6, and a 1. So I'm going to press draw. And I'm going to use red. All right, so I'm gonna write down the numbers I got. I got a 1, a 6, and a 1. So now I can make these 3 digits, and I want to subtract from 1000. And you have 3 rounds. You do have to go the 3 rounds. So I could make 611 and subtract that from 1000, or I can make 116, or I can make 161 like it is right now. So if you had these numbers, what would you do? Take a moment to think about that. I think I'm going to subtract 1000 and I'm subtract 611. So I'm going to do 1000 minus 161. And you can do this in whatever way that you want. Actually, sorry, 611. That's not what I did here. I'm going to go back here. That's okay, right? We made a mistake. 611. I'm going to subtract that. So I'm going to think about 611. I could subtract it a standard algorithm way, right? Which is borrowing and starting from the ones place to the tens to the hundreds to the thousands. But I'm actually going to add up to it. So I'm actually going to think about this. So if I have 611 and I want to get to 1000 in a number line, I might think, well, I know that I need to get from 611 to 700, I know that I need to add 89. Because 89 plus 11 is 100. So from 700 to 1,000, that's 300. So I am now at 389. All right, so now I'm at round 2. So I'm gonna go to round 2 now. This is round 2. So I'm gonna write 389. So I gotta remember that that's where I'm at now. So now I have to roll my dice again. So let's do that. So I'm gonna roll the dice. I'm gonna click the highlight button here. Ooh, went too far. All right, let's start it. All right, stop, stop, and stop. Okay, I have a 1, I have a 6, a 6, and a 1. So let's stop here. Okay, so I have a 6, I had a 6, a 6, and a 1. All right, so now I have to subtract 389. If I do 661 and I go into the negative, I automatically lose. So I think you might know the number that I have to pick, right? Can you think of it? Yeah, 166. So I'm going to do 389 minus 166. So I'm going to do 166 here. I'm going to subtract that. And I'm going to use the standard algorithm. Because look, I don't have to borrow, right? I don't have to regroup or anything. 9 minus 6, that's 3. 8 and 6, that's in the tens place. So that's 80 minus 60, that's 20. And then we have 300 minus 100, which is just 200. So now I have 223. Now I have one more round. So now I'm at 223. So let's roll the dice. All you have to do is click on them. You do have to start the presentation, but all right, let's see. Close my eyes. 2, close my eyes. 1, close my eyes. 3. I got a 2, a 1, and a 3. Okay. I got a 2, a 1, and a 3. So now I'm thinking, what can get me the closest to 0? So look at these numbers. What would you do? I'm looking at this, and I actually think that I would choose 2, 1, 3. So I'm going to subtract. That's 0. That's 1, and that's 0. So that's a score of 10. You got a score of 10. That is pretty good. So again, you can play with by yourself. If you're playing with somebody else, you take alternate turns, and then whoever gets closest to 0 is the winner. But that was actually pretty fun. So that's the game. Right after this, I'm going to stop the share here. But after this, we are going to do the math breakthrough. So have fun. One more thing. If you are going to play, pause the video now and play. Actually, you should pause because you don't need to have a partner for this game. So pause the video, play a whole game, and then come back to the video, and then you'll watch the math breakthrough. All right. Have fun. Bye. All right, I hope you had fun playing Roll and Subtract 1000. Before we move into our math breakthrough, I want to talk a little bit about the question today. It's not going to be a question, it's actually going to be a breakthrough challenge. So there are 2 parts to it. There's one mandatory part and then one optional bonus part. So for the optional bonus part, you are going to need a ruler. So if you want to do the bonus question, you are going to need a ruler. So make sure that you have one ready. So if you want to spend some time to find that right now before you watch the next part, you can go ahead and pause the video, find a ruler, and then come back and hit play.
What do Euclid, 12-year-old Einstein, and American President James Garfield have in common? They all came up with elegant proofs for the famous Pythagorean Theorem, the rule that says for a right triangle, the square of one side plus the square of the other side is equal to the square of the hypotenuse. In other words, a squared plus b squared equals c squared. This statement is one of the most fundamental rules of geometry and the basis for practical applications like constructing stable buildings and triangulating GPS coordinates. The theorem is named for Pythagoras, a Greek philosopher and mathematician in the 6th century BC, but it was known more than 1,000 years earlier. A Babylonian tablet from around 1800 BC lists 15 sets of numbers that satisfy the theorem. Some historians speculate that ancient Egyptian surveyors used one such set of numbers, 3, 4, 5, to make square corners. The theory is that surveyors could stretch a knotted rope with 12 equal segments to form a triangle with sides of length 3, 4, and 5. According to the converse of the Pythagorean theorem, that has to make a right triangle, and therefore a square corner. And the earliest known Indian mathematical texts, written between 800 and 600 BC, state that a rope stretched across the diagonal of a square produces a square twice as large as the original one. That relationship can be derived from the Pythagorean theorem. But how do we know that the theorem is true for every right triangle on a flat surface, not just the ones these mathematicians and surveyors knew about? Because we can prove it. Proofs use existing mathematical rules and logic to demonstrate that a theorem must hold true all the time. One classic proof, often attributed to Pythagoras himself, uses a strategy called proof by rearrangement. Take 4 identical right triangles, with side lengths A and B, and hypotenuse length C. Arrange them so that their hypotenuses form a tilted square. The area of that square is C squared. Now rearrange the triangles into 2 rectangles, leaving smaller squares on either side. The areas of those squares are A squared and B squared. Here's the key. The total area of the figure didn't change, and the areas of the triangles didn't change. So the empty space in one, C squared, must be equal to the empty space in the other, A squared plus B squared. Another proof comes from a fellow Greek mathematician, Euclid, and was also stumbled upon almost 2,000 years later by 12-year-old Einstein. This proof divides one right triangle into 2 others and uses the principle that if the corresponding angles of 2 triangles are the same, the ratio of their sides is the same too. So for these 3 similar triangles, you can write these expressions for their sides. Next, rearrange the terms. And finally, add the 2 equations together and simplify to get AB squared plus AC squared equals BC squared, or A squared plus B squared equals C squared. Here's one that uses tessellation, a repeating geometric pattern, for a more visual proof. Can you see how it works? Pause the video if you'd like some time to think about it. Here's the answer. The dark gray square is A squared, and the light gray one is B squared. The one outlined in blue is C squared. Each blue outlined square contains the pieces of exactly one dark and one light gray square, proving the Pythagorean theorem again. And if you'd really like to convince yourself, you could build a turntable with 3 square boxes of equal depth connected to each other around a right triangle. If you fill the largest square with water and spin the turntable, the water from the large square will perfectly fill the 2 smaller ones. The Pythagorean theorem has more than 350 proofs, and counting, ranging from brilliant to obscure. Can you add your own to the mix?
All right, so that first video talked about the Pythagoras theorem and it being proved with some water. So here's a video of actually somebody doing that. So enjoy.
What is it, the theorem that needs to be discussed here?
A squared equals B squared plus C squared.
Yeah, it's the
sum of the 2, the squared.
the sum of the 2 squares
smaller
equals the sum on the
sides.
hypotenuse.
Yeah,
Exactly.
That
And you can
Big
see
one
that.
should go into the other 2.
So you can see here, the yellow, that's the triangle. These are its 2 sides. And these are the squares of the 2 sides. They're literally geometrically expressed as squares, rather than just mathematically as if that was, say, x. It's just not x squared, but it's literally the square there. And there's y squared. And it's supposedly equal to z squared, which is the longer side, the hypotenuse, because here's the right angle, here, These are not right angles, obviously. There's that. How can we show they're equal? Well, there are all kinds of ways, but here's one way. Yes.
Drum roll, please.
Oh, yes. All right, let's go.
Oh, that's very clever.
There it goes, pouring into the first square.
Wow.
Yeah,
Is he going to fill it up?
Wow.
Oh, well, it definitely equals x squared.
Yeah.
Does it equal y squared as well?
I need to go to the toilet.
There's y squared, it's filling up, it's filling up, it's filling up, it's full. And there it is!
Pretty cool, right? It's super awesome. All right, so for today, we're going to have two parts, right? One mandatory part and one optional challenge part. So for the mandatory breakthrough challenge, because it won't be a question this week, it's a challenge, I want you to find a right triangle in your house. So it could be anywhere in your house, outside, inside. Try to find a right triangle and then show it to us on the Flipgrid assignment. And then if you are feeling up for it, you can actually draw a right triangle and prove that a squared plus b squared equals c squared. So if you want to do that bonus challenge, you can actually draw a right triangle on your math notebook and then measure each side. I'm actually going to do an example for you right now. All right, so I had a measuring tape, which I didn't have a ruler. And so I made a triangle with a side length of 4 inches. This side is 3 inches. And this side is 5 inches. So if this is true, what this should equal is 3 squared plus 4 squared equals 5 squared. And squared, this is a little exponent here. This actually just means that I'm multiplying it by itself. So this is 3 times 3, that is 9, plus 4 times 4, which is 16, should equal 5 times 5, which is 25. And indeed, 9 plus 16 does equal 25. And look, I just proved that the Pythagoras Theorem is correct. Pretty cool, right? All right. Have fun doing it on your own.